Welcome. Thank you for making it. Hopefully we can get something out of these sessions so that we can go ahead and be ready for the AP exam. And again, for those of you guys coming in, you will find our work here in the content library in the section called AP review session. I should hopefully be sharing the OneNote here. And you guys can also follow along on AP Classroom. And so I kind of wanted to see how you guys wanted to go about this. Do you just want me to try to solve these on my own and show you the thought process? Yes, this is for all my classes. This is for all AP Physics 1. So let me know in the chat, do you guys want to have like maybe a minute or so to try to go over the question? Oh no, did my tablet turn off? Give me 1 second. There we go. Okay. Call on one person, then work it out. Okay, just to see what an answer is. Okie dokie. Alrighty, that's one way we can do that. And I was also thinking of running it as a poll here and then seeing maybe about 45 seconds into the poll, see what we think. I know it will be a little rushed. I mean, I may not be able to get an answer to it, but I do think you would like for me to see me solve it first. Okay. In the future, yeah, I was thinking about giving you guys some time to work it out and then explaining the correct answer. We have about an hour. I can go a little bit later, but I don't want to take y'all's time. That's the main concern here.
So, sir, how we usually do in class, like with the
Mhm.
polls and stuff.
Yeah. So I think we'll try it with a poll here and then you get to give you guys some time to work it out and then we'll go over it. I may do a little bit less time just so that we can go ahead and get as many questions covered. I do plan on going over all 21 and it'll be kind of like how we do it in class here. Okay. All right. So let me go ahead and launch the first poll here and we should be able to see what you guys are thinking. And I think I'll keep it at this Zoom level for question number 1. And so we have a 2 kilogram block for mass B, that's 2 kilograms right here. And the question is, what is the gravitational force exerted on block B when it is in this scenario for a block ramp system? Okay, and we'll go ahead and end it here. And so this is a good icebreaker. And so it looks to me like we do know that the gravitational force is given by m times g. This is the weight. And so it's going to be the 2 kilograms times a gravitational field strength of 10-ish meters per second squared. And they say most nearly. And so the best answer here is C. It is hopefully manageable here. So it's question 2 is going to be the same scenario, except they give us a little bit more to this. So let me just try to keep the chat visible here so I can see if we have questions. Okay. And so we'll go ahead and take a look at it. They tell us that it is inclined along a rough surface and the string is tight and it's going to pass over a pulley. And they say that, again, the mass of block A is MA, the mass of block B is MB. And they tell us that at time t equals 0, block A is sliding up the slope as this block falls. And the question is, oops, let me go ahead and admit. The two blocks eventually stop in reverse direction. Which of the following graphs best predicts the acceleration of block A as it moves up and then down the rough inclined surface? And we're going to assume that the positive direction points down the slope. So for this one, you're probably better off looking at it in AP Classroom. And the question is, which of these is going to be the acceleration? And so I'll give us about until 1:20, 1:30 for this one since we just started. Okay, all right, let's go ahead and see here. So if we look at block A, they want us to get the acceleration as this object slows down and starts to slide down. So if we look at the forces acting on this bad boy, we have some tension going up here. We have some force due to friction. and we have some mg sine of theta. We have some component of the weight acting down the ramp. And this is when it is going up the ramp. So we could say up, on the way up. On the way down, and this is all for block A, okay? So on the way down, so this block has been sliding up, it slows, comes to a stop, and begins to slide down. And so they tell us that they want us to get the acceleration for the person that just came in. And we still have the tension acting up on the way down. The string is still pulling it up. And we still have mg sine theta acting down, the component of the weight along the ramp. But now that it's sliding down, friction is opposing this slide. And because this thing is sliding down, the force of friction has changed direction. So this is the main difference between these two. The force of friction changes direction when it is moving up to when it is moving down on the ramp. And the net force is going to depend on these forces here. In this case, we have two forces causing me to slow down. Here, in this case, I have one force causing me to speed up and two opposing me, okay? So what's going to happen here is the friction is not going to be constant because we have a net force here of T minus the force of friction minus mg sine theta. And then we could divide it by the mass, but we're not going to worry about that. In this scenario, the net force in the direction that we're moving it is mg sine theta minus the force of friction minus the tension. So when we look at these, they tell us that positive is down the ramp. So we had a larger force acting down the ramp when we were sliding up because friction and our weight are acting down the ramp. When we're sliding down, we have one force causing us to accelerate downward, and it's a little smaller force. So here we have two forces acting down the ramp. Here we have one force acting up down the ramp. And so our best answer choice here is B. Maybe we were thinking C. But in this case, down here, this would be a direction negative equals up the ramp. They told us that they considered the positive direction to be down the ramp. And the entire time, up the ramp, they told us that we are going to consider down the ramp. And so up the ramp would be a negative acceleration in this scenario. And so this is a pretty good answer, but not quite because of the direction here changing. The acceleration is always down the ramp. It's more because we slow down and we have two forces acting down. And then when it's sliding down the ramp, friction changes direction and acts up the ramp, decreasing the downward force. This might be, well, this is maybe like a graph of the velocity, but the velocity should be constantly changing. It's going to have or not even a constant slope, sorry, because the acceleration isn't constant. What is the name? Oh, so this is going to be unit 2. And it's going to be the progress check. So we're going to have two different slopes. This would be the velocity. So B is our best answer choice for this one. Any questions over this? Just because this question is a little tricky. It's kind of dirty or nasty. And you can continue, you could either type it or speak up. We'll go ahead and jump to question number 3 here just real quick to continue the ball rolling. So they tell us a 5-kilogram object is released from rest near the surface of a planet such that the gravitational field is considered to be constant. So the value for the acceleration is the same throughout. The planet the mass of the planet is unknown, so we can't use Newton's law of gravitation. But we do know that after 2 seconds, the object has fallen 30 meters, and air resistance is considered to be negligible. What is the gravitational force exerted on the 5-kilogram object near the surface? Let's see what we're thinking. Dang, dude, 17 people, I'm surprised. All right, I'll call it once we get 10 answers. Just to try to give the bulk of the people a chance to answer. All right, we got 11. And so most of us are thinking D. Let's go ahead and see here. Well, we know that the displacement, the magnitude of it is going to be 30 meters. And we know that the time it took was 2 seconds, I believe. Let me just move the poll here. The other thing we know is that it is released from rest. So the original velocity here is 0. So we can go ahead and if we rearrange the displacement equation, because the original velocity is 0, this part doesn't really matter. And we can go ahead and you are allowed a calculator, so you could end solve this if you wanted to right away. Or you could just recognize that if you do your algebra real fast, we get the time. Sorry, not the time. We're looking for the acceleration. The acceleration is given by 2 times the displacement all over the time squared. And so this will be the acceleration due to gravity. And so we've learned that m times g is the gravitational force. So the acceleration due to gravity, which we call g, can be calculated through this approach. And that's going to be 2 times 30 meters all over 2 seconds quantity squared. And we get 60 over 4. That's 15 meters per second squared. Let me make sure. 4. Yeah, we can cancel out one of the 2's, but then we still got to divide by 2. So that's 15. So then the gravitational force is going to be 5 kilograms times 15 meters per second squared. So this is going to be 50 with 25 for 75 newtons. So I believe our best answer here is D. Let me know if you have questions. Welcome, Mo. If you want, you can follow on AP Classroom. There is going to be a recording of this, and you will find the solutions for our work here. And I should recall this or retitle this AP review sessions, but it will be in the content library. Plot twist, these are the answers to your homework that I'll be assigning for next week. Okay. Any questions so far? We had a couple of students thinking 37.5. Let me know what you think your error was here. Or maybe I made a little mistake here in my math, but I'm thinking it's D. I could be wrong, right? Like we've seen throughout the year that is the case. And then 15, maybe what we were thinking is let's take the 30 meters divided by 2 seconds to get 15. Actually, that's bad. We actually end up getting the same numbers even if we do the math process or the thought process wrong. It just works out that. You use 5 times 15, so I don't know what so you just kind of maybe multiplied it a little incorrectly. Did I multiply that correctly? 50 and then half of 50 because of the 5 is 25. Okay. Let's go ahead and look at this next one here. Question number 4. A block of mass M is attached to a modified Atwood machine. And an Atwood machine is basically a pulley, a block, and usually another block falling. But in this case, we're going to pull it with a certain force. And is accelerated at 3a by a constant force. And the question is, what is the weight of the block? Which of these is going to give me the weight of the block? Oops. Let me try to get the scroll here just right. Okay, we're going to go ahead and relaunch the polling. Let's see what we're thinking. Oh, did I bring my water? Yes. Stay hydrated, homies. First blood, we have an answer. Okay, and I'll give us to about 45 seconds to go ahead and look at this one. All righty. So most of us are thinking B because maybe we're thinking 3A. But well, how do we calculate the weight of a block? That's the force due to gravity, which is just mg. So D is our best answer choice here. Another one of those weird AP questions. Now, I don't know if you'll get something like this. I hope they kind of stop doing this, but it on some level really tests your understanding, because we should know that the weight is calculated by M times G, and this here is just kind of there to throw us off. There is another way that we could go ahead and calculate the weight. Because if we look at the free body diagram of this, we have our tension, which happens to be the force that they give us. And we do have the weight mg. And if we do Newton's second law, we get the pulling force transmitted through the rope, Fo, minus mg equals m times a. And in this case, the acceleration is 3a. So we could rearrange this, and what we find out is Fo minus Fa, if I move that over here and this guy over there, sorry, minus 3ma, or 3a, m times 3a. This would be another way to calculate the weight. Mg would be given by this expression as well. But if we look at our answer choices, well, mg is just mg, that's the weight. If this guy had a little 3 and an a instead of g, this one would work out. But these don't. No matter what, under any circumstances in this case, if they ask what is the weight of the block, it's not 3 mg, it's not 2 mg, it's always mg for a constant gravitational field. And again, let me know if there are any questions. Share them in the chat, speak up. Let's go ahead and look at the next one here in the meantime. Here's a fun ride. Have you ever been to Fiesta, Texas? Ooh, rage quit. No, just kidding. They're like, I'm done with this. No, internet issues most likely. So the amusement park ride, as shown above, takes riders straight up a tall tower and releases an apparatus holding the seats. The apparatus free falls to the earth and is stopped right above the ground. Which of the following indicates the magnitude of the gravitational force exerted on a rider of mass m on the way up and on the way down? Let me go ahead and get this scroll here. Relaunch polling. Let's see what we're thinking. Yeah. Okay. So it does appear that we are learning. And so they are asking strictly about the gravitational force, not the force exerted by the seat. These are two different things. The gravitational force is just mg. And so I weigh mg on the way up and on the way down, okay? So my weight does not change near the surface of the earth. I am just on the way up. I definitely feel heavier, but that's because of the push from the seat. And I feel lighter, but these are feelings. These are not actual forces. You get these feelings due to acceleration. When you accelerate up, you feel heavier down. When you accelerate down, you feel lighter, as if you are weightless. So this would be better if they asked the answer, or this here is the force exerted by the seat. Which is true. The seat definitely exerts more force to accelerate you up. And if you're falling with the apparatus, the seat doesn't have to exert any force on you. It's just going to be free fall, and you're going to be, falling due to the force to the gravity exerted by the seat. Okay, so hopefully that made sense there. All righty, let's go to the next one here. We have planet X, planet Y. Oh, and the answer choices are down here. Let's see here if I can kind of zoom in and have it all visible. Question 6. So we have planet X. It looks to me like identical spheres are dropped. Oh, come on there. There we go. From a height of 100 meters above the surfaces of planet X and planet Y. And it's in meters. The position of the spheres as a function of time is recorded as the spheres fall. These data are shown in the graphs above. Which planet exerts a greater gravitational force on the sphere? And let me try to scroll over here. Where's my scroll bar? There we are. And what evidence supports this conclusion? So let's go ahead and see here what we're thinking. Dang, dude, it's already 6:20. A little surprised. Okay, we have about 10 responses. Go ahead and call it at 30. Very nice. All righty. And so we'll go ahead and share the results. And so most of us are thinking D. So let's go ahead and see here. Well, if I'm going to experience the same displacement, then if we look at the acceleration we saw was given by twice the displacement over the time squared. This is the displacement equation rearranged for acceleration when the original velocity is 0. So if we look at this will get bigger when this gets smaller, because not alpha, because the acceleration is proportional to the inverse of time squared. So the smaller the time, the faster I'm going to be moving through here, the greater the acceleration. So if we look at this, we make it in about 4.5 seconds or so, compared to 6 seconds. So that's one way. Now, how do we explain that here? Well, if we look at this, hopefully we see that planet Y. And now here they say because the magnitude of the slope of the curve increases at a faster rate. We're going to be going the same speed by the time we fall. The slope here is going to be the same in both of these because the slope is the velocity of a position time graph. So we start out with 0 slope and we finish with some slope. And we are going to reach that slope faster. We're going to do that in less time than this guy. And that's what this guy is saying. We will reach the same velocity, but on planet Y, we reach that velocity sooner. Let's go to number 7. And I don't think I can zoom in here. Let me zoom out. And you guys are probably following along an AP Classroom, so hopefully the formatting works better there. 2 identical blocks, block A and B, are placed on different horizontal surface. Block A is initially at rest on a smooth surface, and block B is initially at rest on a rough surface. A constant horizontal force of magnitude F naught or F sub 0 is exerted on each block after the force has been applied for some time. And so as soon as we see force and time, we should be thinking impulse generally, but we don't need to do that here. This is unit 2, but on the AP exam, you're not going to know if this is a unit 2 question or a unit 5 or a unit 6 or whatever. So when impulse acts on an object, it changes the velocity. And the speeds of blocks A and B are VA and VB respectively after this time. Which of the following claims indicates the correct relationship between VA and VB and provides the best justification for that relation? Maybe some of you guys are getting ahead and trying to answer some of these. Very good. I think I learned the best in college when I would do that. I try to answer ahead of time and then listen for the explanation, especially if I was wrong, because you really want to fine tune your thought process. Where did you go wrong? All righty. We'll go ahead and call it here. And so if we look at this scenario, because block A is on a smooth surface and block B is on a rough surface, we should recognize that block A has no force opposing its motion. It's going to have the full force acting as the net force. It's going to have a greater acceleration. And that's because there's no friction on A. So we should expect the velocity of A to be greater than the velocity of B. Here they say the forces between the atoms in the block and the atoms in the surface oppose the motion of the block and are greater on average for block A. Well, this sounds true. This sounds exactly like the description of friction. The problem is they're telling us that this friction is greater for block A. No, the force of friction here on block B is some number, but the force of friction on block A is 0. So really good justification until the end. They had us in the first half. And so our best answer choice here is D, because the forces, friction, of the atoms between the block and the atoms in the surface oppose the motion of the block and are greater on average for block B. Very good. Most of us were thinking D. Okay, let's go ahead and look at number 8. Which of the following experiments could be used to determine the inertial mass of a block? Let's see what we're thinking. All right, we'll go ahead and end the polling here. All right, excellent participation. And so we have a bit of a distribution in the answers, B, C, and D. Now, what we have learned is that gravitational mass is the same thing as inertial mass. Experimentally, this has been proven. But there are two ways to get these two experimentally. Gravitational mass is the mass in m times g. Inertial mass is the mass in m times a. And in free fall, if we measure things out, we find that the resulting acceleration is the acceleration due to gravity. And that means that these two numbers m would be the same. So we need to find a scenario that talks about acceleration and not anything having to do with gravity. So let's go ahead and see B. Drop the block from different heights, measure the time of fall for each height. This is going to give us more of the gravitational mass. We still need a couple of things here for this experiment, because well, actually we could get A from this, right? A is 2 times delta x over t squared. So once we have the acceleration, we could compare that and get the gravitational mass. So it sounds good. It will give us a mass, but it'll give us the gravitational mass. Place the block on a rough horizontal surface. Give the block an initial velocity and let it come to rest. Measure the initial velocity and measure the distance that the block moves in coming to rest. So this could work. Let's go ahead and see if D is a little better. Use a spring scale to exert a force on the block. Oh, we now know the net force on the block. Measure the acceleration of the block and the applied force. So now we have the net force. And then if we divide that, by the acceleration, we get the mass. So D's are better answer. The reason why this one doesn't work is all this gives us is the acceleration. And you may be wondering, how do we do that? Well, we can use the v squared equation. And all we know is the acceleration in this case. We know that this would be 0. But we still don't know what the net force is. We would expect it to be friction. And the force of friction here would be mu times the normal force, which would be equal to mu times m times g. The thing is, to get the friction force, we either need to know m, or we need to find a way to measure it so that we could solve for m. So sadly, this one won't work because we don't know exactly how to get that force. We get the acceleration, but we don't know the force. This is partially correct. And so that's why D is our better answer. It gives us both things we need. All righty. Question 9. A 1,500 kilogram car traveling along a road is hit by a 0.1 kilogram rock that exerts a small or creates a small crack in the car's windshield. Which of the following describes the interaction between the windshield and the rock? Dwayne Johnson. All right, we'll go ahead and call it here at about 20. Oh, damn, we're going to get just about everybody. Oh, this is being recorded. I probably shouldn't say that. Okay. Yeah, well, so it goes. So most of us are thinking D. So hopefully we remember the bug in the car, Mr. Self-Destruct. Because as soon as there's an interaction between two objects, Newton's third law procs. These forces come in pair. The force on the rock by the windshield is equal and opposite to the force on the windshield by the rock. This is weird because what we see is the acceleration, and that leads us to believe that, well, the car didn't really change its velocity. It was the rock that got deflected. And so it had a larger, it appears that it had a larger force, the rock, but it's not the case. Regardless of how fast you go, regardless of how big you are, the moment you come in contact with an object, you share a force, and those forces will be equal and opposite. So D is our best answer choice here. The rock exerts, but the car does not exert a force on the rock. Sorry, really important. Forces always come in pairs. And this is testing, do you know the relationship between the action-reaction pairs? 10. Two objects, X and Y, move toward each other and eventually collide. Object X has a mass of 2m and is moving at a speed of 2v original, or v sub o, or v naught, to the right before the collision. Object Y has a mass of m and is traveling at a speed v original to the left. Which of the following describes the magnitude of the forces F the objects exert on each other when they collide? Okay, we'll call it here in about 7 seconds. All righty. So really important, what we were just saying, Newton's third law says the forces have to be equal and opposite. So this is out, this is out. If this was 4F and 4F or 2F and 2F, maybe we would consider them. But because they are opposite or different magnitudes, not the case. Newton's third law here is applying. They must be equal. And they got to be in opposite directions. It looks to me like X is moving this way. X gonna give it to you. Rest in peace. And Y is going to be moving this way. And so it looks to me like X is going to exert a force on Y in this direction. The force on by Y on X is going to be in this direction. So the force exerted by X on Y is to the right, and the force exerted by Y on X is going to be in the opposite direction. Well, bam, there we go. Okay, so very good. Let's go ahead and look at number 11. And let me know again if we have any questions. A block is placed on an inclined plane and remains stationary as shown in the figure above. A student claims the block remains stationary because as gravity tries to pull the block down the ramp, the block exerts an equal and opposite force on itself up the ramp. Is the student's claim correct? Justify your answer. Oops. Oh, it's set to snap. Let me relaunch the poll. So we're kind of making adequate time. We're on number 11 at 6:34. We should hopefully finish right around 7. Let me know if you want me to go faster or slower, or this is a good pace. Okay. All right, we'll go ahead and end the polling here. So really important. This is one of the big things that is not like necessarily explicitly tested, except here's a question that finally does, but really important. An object cannot exert a force on itself. And I've been saying this a couple of times through our lessons as explanations, but maybe we've missed it or not. An object cannot exert a force on itself. A net force, to be specific, on itself. An object cannot cause itself to move. There's no such thing as self-action. No self-action. So the student is incorrect. Newton's first law states that the block's inertia must cause it to move. No. And then no. Newton's third law says that the block cannot exert on a force on itself. And really here they should be saying a net force, because let me push on myself. I push on my chest pushes on my hands, but overall those two forces are equal and opposite. They cancel out. Yeah, the wording gets you, and you were thinking the normal force. Yeah, they're taking advantage of that. Here, the only way for this block to remain stationary is probably because there's some force due to friction acting down, because this guy has mg, sine of theta, its component its component of weight along the ramp acting down. So yeah, it's a little difficult. Try not to read too much into it and just take explicitly what they tell you there. Because we're thinking, well, the block is pushing down on the ramp and the ramp pushes up with a normal force. So an object cannot create a net force on itself, because the moment it pushes on itself, it pushes back on itself. Those two forces are equal and opposite by Newton's third law, and we'll have that. Number 12. Students connect a spring scale to a block on a rough horizontal surface. The students use the spring scale to measure the magnitude of the horizontal force needed to pull the block a constant speed. Which of the following statements explains why two forces exerted between objects are equal in magnitude? And then welcome, I think that was Mario who came in. Welcome. You can find our solutions here in OneNote. You will find it in the section called Content Library, AP Review Session, Multiple Choice A. And you can also follow along on AP Classroom.
Okay, thank you, sir.
I will be providing a recording of this after the session, so hopefully we can make, resources for those that are not here. All right, we're going to call it here in 2 seconds. So let's go ahead and see here. Which of the following statements explains why two forces exerted between objects are equal in magnitude? The gravitational force and normal forces exerted on the block because they are Newton's third law pair. Ooh, sounds like a big gotcha. Remember that the action-reaction pair for the force due to gravity. So when I have an object, the force due to gravity by the Earth on the object, its action-reaction pair is the force due to gravity by the object on the Earth. And this sadly is doing away, this is doing this goes against probably everything you were taught in AP or pre-AP physics or IPC. You were taught that the normal force is an is a reaction to you putting a block on it or an object on it. It does react, but it is not the action-reaction pair. The Earth gives this object weight, and this object gives the Earth weight. And that weight is the same force between them, or really gives a force that we call weight. So A is a big gotcha. B, the frictional force and the force exerted by the spring scale because they are a Newton's third law pair. Oh, this also sounds good, but the way I see it is the spring scale is pulling on the block and the block pulls on the spring scale, and that's the action-reaction pair. The friction force action-reaction pair, well, there's a force of friction on the block, and then the surface has a force of friction that is its action-reaction pair. So you always want to match the two objects to, like exerting a force on each other for these. So I don't think this is it. The normal force and the friction force. Automatically, I'm thinking no, not the case. This is almost never the case. No, they're not always going to exert forces of equal magnitude on each other. And if we look at the results, yeah, there was one person who submitted an answer for that one, but it was in the minority. Turns out D is our best answer choice. Frictional forces that the block and the surface exert on each other, because objects always exert forces of equal magnitude on each other. And so here we're talking about objects in contact with one another. So I think they could have worded this a little better. That's how we want to consider, well, even then, like the force due to gravity is not a contact force. I'll refrain from writing that here. Okay. So just like the surface pulls against the block is pulling against the surface. It's this wording technicality. I'm not a good test taker, but you're working on it. These questions feel so simple, but I still find a way to get it wrong, dude. Same here. It would happen to me. I wasn't always like the best physics person. Language for me sometimes gets in the way. So I'm glad you're seeing that they are simple or they feel simple, because that's part of the learning. And part of it is, yeah, doing these questions so that you can get a feel for how they're being asked. So for instance, like here, oh, well, I have a water bottle, whatever, brand doesn't know. Let me hide the brand, right? So gravity is trying to pull this water bottle down, and I'm exerting a force through friction on my hands to hold it up. But really important, the action-reaction pair is not the friction in my hand with the weight of the bottle. The weight of the bottle's action-reaction pair is, again, the gravitational force that the bottle exerts on the earth. We don't see it, but when I let go of this bottle, the bottle accelerates down towards the earth and the earth accelerates up to the bottle. It's just that the earth is so much more massive that its acceleration is near zero. It's like 10 to the 24, 10 to the negative 24 meters per second squared, around there. In this case, the action-reaction pair for the friction by my hand on the bottle is the force due to friction on my hand by the bottle. So you always want to match the two objects that we're talking about for Newton's third law. Sorry, that was a lengthy one. A spring-loaded launcher has a mass of 0.6 kilograms and is placed on a platform 1.2 meters above the ground. The force of friction is negligible between the platform and the launcher. The launcher fires a 0.3 kilogram ball and it lands a distance d to the right of the platform, as shown in the diagram above. Which of the following explanations is true? I'm trying to get this in view for you. Okay. So this one may be a little funky here. We didn't do too many recoil problems when we were doing momentum. I mean, we don't need to do a recoil problem, but it helps. Okay. All righty. And so we only have about 5 submissions. Yeah, this one's taking a little bit more time. We'll go ahead and call it here just so that we can try to get the explanations. Okay. So as we fire this ball is going to gain some velocity due to the force that the launcher exerts on the ball. And it's going to gain a velocity due to an acceleration. So the force that the launcher provides on the ball divided by the mass of the ball is going to give us the acceleration of the ball until they're done firing. And we've learned that the sideways velocity remains constant once it's in the air. Sure, I'm pushing this guy and it's accelerating, but the moment I lose contact with it, there's no more force. So we need to compare the velocities of these two after they're done recoiling. Well, the launcher, the mass of the launcher is 2 times the mass of the ball. What this tells us is that if we do Newton's second law, the acceleration is the force divided by the mass. And if I have twice the mass, then I'm going to have half the acceleration while we are separating. Which means that I am going to have half the velocity in that same amount of time. So I believe that C is our best answer choice. Wait, did I get these correct? 0.3, 0.6? Okay. The mass of the ball is 3 times less than the mass of the system. Oh, okay. I believe C is our best answer choice. I can check real quick to make sure because I could have fumbled here. Okay. No. It is C. Just making sure. Because it sounds pretty good, right? The mass of the system. This statement is true, but we got to think about the force here and the action reaction pair. And so the force is the same between both of them, but one has half the mass, so it has twice the acceleration. So it picks up half the speed or twice the speed. That's the other. Okay, let's go to number 14. Okay. A student pulls a block over a rough surface with a constant force Fp that is at an angle theta above the horizontal as shown. If Fp remains constant, but the angle is increased, which of the following is true sometime later? Okay, you have to go eat, have fun, enjoy your meal. Hopefully it's tasty. Sorry, I didn't see that until right now. You probably left already. Oops. All righty, we'll go ahead and call it here. We have about 9 submissions. That's pretty good. All righty. So let's see here. So hopefully we recognize the weight of the block will not change. It's always mg. So it's really just a question about, well, what's going to happen to the friction? Well, if the angle increases, let's go ahead and take an extreme case where I'm pulling straight up. Ooh, FP, not B. If I pull straight up, I might be able to lift this guy. And if I lift it, it's no longer in contact and I would have no friction. Another way we can think about it is the force of friction is given by the coefficient of friction times the normal force. As theta increases, the vertical component of Fp, so Fp in the y direction increases, which means that I am lifting more and more up. I am taking it off the surface, so the normal force will decrease. So that goes down and that goes down. Let's go to 15. It's going to be a buzzer beater. A satellite orbits Earth. The only force on the satellite is the gravitational force exerted by the Earth. How does the satellite's acceleration compare to the gravitational field at the location of the satellite? There are 2 answers here. We will only be able to choose one of the 2. Sorry, I'll try to get the other poll here. Oh, why does the normal, so remember that the normal force is like the force that the surface provides on an object resting on it. So let's say for whatever reason, your sister's sitting on you. If someone starts to lift your sister off of you, you'll feel less force pressing on you. So you'll press or push back with less force. And then, yeah, it's okay if you go have fun with your dinner. Take it easy. Let me know if that answered your question there. But the normal force is the force needed to hold an object up. If something or someone else exerts an upward force, then I need to exert less force to hold it up. And so it's going to get lighter and lighter, or not lighter and lighter, but it's going to press less and less into that surface, decreasing the normal force. Let me know if that answered your question there. And so plot twist, it's one of the Nambudiri, sorry. Okay, so the correct answer here is C and D. So really important. The acceleration due to gravity is the gravitational field strength. Acceleration due to gravity. Yeah. And I don't know if you got my response there, Marcela, but yeah, totally fine. Thank you for stopping by. And this is what we call the gravitational field strength. And what we find out is that experimentally, mathematically, theoretically, these 2 quantities have the same value. They are the same thing more than anything. Not that they just have the same value, they are the same thing. And the acceleration is going to point towards the Earth. The gravitational field strength will point towards the Earth. So they have the same direction and they have the same magnitude. They are equal. And again, let me know if we have questions over this one. 16. An object is at rest on the ground and experiences a downward gravitational force from the Earth. Which of the following predictions is correct about why the object does not accelerate downwards? So like 2 answers justify your selection. So here we can get 2 of them. Okay, we'll go ahead and call it here. All righty. So from the looks of it, A and B are our most popular answer choices. So why does it not accelerate downwards when there is this downward gravitational force? So we should be thinking, well, if it's not accelerating downwards, we need a force acting up. So let's go ahead and look at B. The normal force is exerted upward on the object from the ground with the same magnitude as the gravitational force downward on the object. That's one of them. Bingo. A. The bonded molecules of the object. So this is just like really wordy for just saying, yeah, the molecules of the object are repelled upward by the bonded molecules of the ground with the same magnitude as the gravitational force downward on the object. So upward. Bam. There we go. We had an answer for C, or a submission for C. The bonded molecules of the object are attracted downward. So really important. All objects, when in contact with each other, exert a force because of the repulsion of their electrons. On the surface of these guys are electrons, and as we try to bring them closer and closer to each other, hopefully in chemistry you learn that opposite charge or similar charges repel. So the electrons of my hand, on my left hand, and the electrons of my right hand, they're repelling each other. They are not attracted. If they were attracted, they would bond, and that's what glues essentially do. 17. A student uses an electrical force sensor to study how much force the student's finger can apply to a specific location. The student uses a finger to apply a force on the sensor and collect data from 2 trials shown in the table. During which trial, if any, let me just go ahead and get this one. If any, does the student's finger experience the greatest electromagnetic force? Okay, we have about 10 responses here. We'll go ahead and call it at 30. All righty. So this is kind of weird because we may be wondering, well, what the heck? We're in mechanics, not electricity. Like, why are we talking about electromagnetic force? This is the repulsion of electrons. The Coulomb force, as they call it. On the surface of touching objects. And depending on how you define it, things don't really touch because the electrons repel each other, but we might as well consider it touch. So if we look at this, if I'm not pushing on the sensor, then the sensor has no reading and I'm not in contact with it. So if there is a reading, then I am in contact with it. And that's because my electrons are pushing that sensor inward. So trial 2 is the larger force applied to the sensor. So let me know if you guys have questions over that one, but it's kind of like, I don't know, I think it's kind of like a weird question. But it's very important to recognize that one of the reasons why we have Newton's third law is because these repulsions that allow contact. If I'm not in contact, there is no repulsion, there is no electrical influence between these surfaces. I mean, here, even though my hand is not touching the screen, there is still an electromagnetic repulsion. It's just, it's so weak, we don't really sense it. But if you've ever put your hand up to an old-timey television, you can feel this tingling sensation as you bring your hand closer and closer to the screen. And that's because the electric field of the TV is exerting an electric force, and the electrons themselves of the TV are repelling your hand, and it's more noticeable. 18. A toy car has a battery attached fan to it such that the fan creates a constant force that is exerted on the car so that it is propelled in the opposite direction in which the fan blows air. The car has a carriage that allows the student to attach objects of different masses as shown above. The fan has only one speed setting. All frictional forces are considered to be negligible. Which of the following procedures could be used to determine how the mass of the fan car object system affects the acceleration of the system? Okay, all righty, so let's see here. So in this case, we want to see a relationship between the mass and the acceleration. So let's see here. Measure the mass of the system using a balance. Sounds good. So all of these start out pretty good. Activate the fan. Okay. We'll see here because this one's a little different. Measure the distance traveled by the system at a known time by using a stopwatch and repeat the experiment for several trials. Well, because it has one setting, there's only going to be one value for the force. The force in this case is constant. So we can go ahead and change the mass and get a relationship where the mass is going to be, like the change in mass is going to be inversely proportional to the acceleration. F equals m times a. So if that goes up and this is constant, we can treat that as a 1. It's not going to change. Then that has to go down. So we want to make measurements of the mass and the acceleration. We can get the acceleration by using displacements in time. So I think A is a pretty good answer. And we want to repeat for several trials. Let's look at B. Measure the mass of the system using a balance, activate the fan, use a meter stick and a stopwatch to measure the initial and final speeds of the system. This would be really hard. We can't actually get measurements of final and initial speeds. I mean, it might be 0 at the beginning, but I doubt it because the fan is already turned on. Unless we have a motion detector, we can't directly measure speeds. All speed measurements are actually derived by some kind of sensor taking a tiny change in position and dividing it by a tiny change in time. Because getting instantaneous values for velocities is really hard. And unless you have a function, you have to do, like, you can't get those numbers. If you have a function, you do calculus. But this, I think, is not very good. Connect the spring scale to the back of the car, measure the amount of force required to hold the system at rest. In this case, if it's at rest, the acceleration is 0. There's no relation there. And so, yeah, answer choice A is our best, answer. I feel like I've seen this one before. I think I asked this question once before. I can't remember. But yeah, I definitely asked this several times last year because it's kind of like a weird one. Because I really wanted to drive the idea home that you can't really get measurements for speeds. They're derived from measurements of position and time. At time t equals 0, object X of mass m travels at a constant speed of 2 meters per second to the right toward an object Y of mass 2m that is a distance 8 meters away from object X while at rest, as shown above. Both objects are on a horizontal surface where the frictional forces may be considered negligible. Which of the following pairs of force diagrams represents the forces exerted on object X and object Y at t equals 4 seconds? We're almost there. Ya merito. We're going to be short by about a minute or two. And so here, I think, yeah, it's probably best to maybe go into AP. Oh, well, here we can see it. Okay. And so we'll go ahead and start talking about this one. And so if we look at this, object Y has twice the mass, so it should have twice the gravitational force. So we should be looking at this scenario. And so all of these are pretty good so far. The normal force should be the same vertically because these objects are not accelerating vertically. And when we compare the forces, we have learned by Newton's third law, these forces have to be equal and opposite. This one is 2 squares, this is 1 square, that's out. This one is 4 squares compared to 2 squares, that is out. They have to be the same here. Very good. Most of us were thinking B, Newton's third law. Now, we don't know how these guys are in relation. We don't know the gravitational force and the force from Y are going to be the same value. Kind of like here, it just so happens that they're both 2 squares in each direction. But the important thing to recognize is the vertical forces balance out. And by Newton's third law, the contact forces have to be equal and opposite. Number 20. A student sets up an experiment to determine the inertial mass of a cart. The student has access to the following equipment: a spring scale, meter stick, and stopwatch. The student uses a spring scale to pull the cart starting from rest along a horizontal surface such that the reading of the scale is always a constant value. All frictional forces are considered to be negligible. In addition to the spring scale reading, which of the two following quantities could the student measure with the equipment to determine the inertial mass of the cart? We'll go back and pull my poll, relaunch polling. Yeah, sorry. We're going to be like maybe 5 minutes over. Sorry, I underestimated. Okay, we'll go ahead and call it here. So we want to measure to determine the inertial mass. And so we've learned that the net force is equal to the inertial mass times the acceleration. So we need to find ways to get the net force. Well, that's the scale. The net force will give us a spring scale. And we need to find a way to get the acceleration. The problem here is with these three equipment alone, we cannot measure the acceleration of the cart. That is what we want, definitely. I agree. But we cannot measure that given the equipment that we have. We need to measure the total distance traveled and the time during which the cart is in motion to get the acceleration. The acceleration would be twice the displacement over time squared. So C was our most popular answer choice, but it's kind of a gotcha, okay? Because we need to measure these other two things with the equipment that we have. We do not have an accelerometer. If we had an accelerometer, then maybe we could measure the mass, the acceleration. Let me know if we have questions. Yeah, it's a 2. Yeah, it's a select 2 answer. Sorry. Which I only gave you guys a multiple choice. Sorry about that. Yeah, that could have also helped you guys determine the answers there, right? My bad. Okay. 2 students, student X and Y, stand on a long skateboard that is at rest on a flat horizontal surface as shown. In order to get the student-student skateboard system to accelerate, student X claims that student Y should apply a force on student X while both students stand on the skateboard. Which of the following statements is true regarding the claim made by student X? Let's see here. For all the marbles, what do we get? Sorry, I don't understand DW. Enlighten me. Oh, don't worry. Okay. Man, you kids and your lingo. All right, we'll call it here in 5 seconds. Okay, all righty. So The claim is incorrect. We cannot exert a force on each other. Both students are internal to the student-student skateboard system, and the internal forces within a system cannot cause a system to accelerate. Very good. Most of us were thinking D. All right, Newton's second, and this is the annoying thing. This second part here is proper physics. Newton's second law does state that an object accelerates if a net force is applied to the object. But the moment one person pushes on the other, these forces are equal and opposite. So the net force is 0. So the first half is wrong, but the reasoning is correct physics. It's correct because student implied, this is not true. We cannot exert a greater force. Even though we can exert a force greater than friction, the net force will still be 0 because the moment she pushes on her, those forces cancel out. Okay, all right. That's it for today. Thank you for stopping by.